Okay, I think it's time to start. It's almost 10 o'clock a.m. Central Time. We welcome all of you to this event organized by the DSI, Qatar DSI Chapter. We would like to welcome all our audiences from, the region, as well as from, United States. We have also a few participants. Okay, my name is Khalid Al-Sher. I'm the secretary for the Qatar DSI Chapter. This is our second event organized by this new chapter. We have been established since just August 2020. We had a workshop also by Dr. Victor from North Texas in March, and this is our second workshop. We're glad to have, Professor Ned Koch will speak about structure equation modeling with, WarpPLS, the software that he has developed and publishing in top-tier decision science and information system journals. I will have just 2 minutes introduce, Ned, and also, briefly talk about the chapter, and then we'll have, the workshop. I encourage you, if you have not done that so far, if you install the software, because it will be hands-on, it will take maybe less than 5 minutes. I send, the link. It's very simple, WarpPLS.com. Straightforward, it's not, it will not take much time. Okay, recently we have, as you can see, if you explore Decision Science Institute, the homepage, you will find under Explore DSI, we'll have, the regions in the United States, as well as the recently established 2 chapters, which is China and in Qatar. And also, we recently also developed the homepage, okay, for our chapter, which we have, some information, especially for our participants in the region, so they can join the chapter, okay, by attending the National DSI Conference and designate Qatar Chapter as their affiliation. Okay, based on the mission of National Decision Science Institute, our mission also to provide a forum to exchange research ideas, providing teaching and professional development opportunities in the decision sciences related field. Typically through organizing such like what we are doing today, workshops, seminars, and also in the future, we plan to have a regional conferences. This is the main aim of the chapter. For more information also on the website, you can contact any one of the board of directors, the president, Dr. Khalid Abdel Qadir, or myself, or Dr. Nuruddin. All this information also on the website you can. Okay, coming to our workshop, as I mentioned, we are glad to have, Professor Koch from, Texas A&M. Professor Koch is a Texas and A&M Regents professor, and he is the chair of the Division of International Business and Technology Study at Texas and A&M International University. He holds a degree in electronics engineering, computer science, master, and management, PhD in management. He has authored and edited several books, including the SAGE publication book titled system analysis and design fundamentals, a business process redesign approach. Also, as you can see on the screen, he has published a number of journals in high-impact journals, including Communication of the ACM Decision Support System, European Journal of Information System, among others, just to save the time. Also, he is the developer of the, this software that today we will have the workshop, which is WarpPLS, widely used for structural equation modeling. And I think maybe I will be biased because I have used, Literal, I have used AMOS, PLS. To tell you the truth, just I was exposed to WarpPLS, not in intensive, but I can, at least have testimony that it is very user-friendly. This is what, and you can see through this workshop. I will not take much time. We will let, Ned to start the workshop. It will be hands-on. And also at the end, or maybe during, if you have any question, we will monitor the chat because I think you are on mute during the workshop, but you can raise any question in the chat. We will monitor it. Without further ado, Ned, the floor is yours.
Thank you, and I will occasionally I'll say, Khaled, are you listening to me? Are you being able to hear me? Just to make sure that we're connected, and I don't go like 30 minutes talking to the computer and nobody's listening. So just to make sure that things work, I have a couple of things here set up so that if my internet connectivity goes down, I will switch to my personal hotspot on the phone, and I will connect back anyways, just in case. So these are some contingency issues. So let me share the screen now. Yeah, I'll share the entire screen. Okay, good. Here we are. Let's see if I can switch. Okay, here we are. So I wanted just to say that I was born and raised in Brazil. I actually went to electrical engineering school here in Curitiba. Then I went north to close to São Paulo to study computer science. Here in Curitiba, I studied one of my favorite topics was actually numeric computing. And that's something that we use a lot when we develop software that implement algorithms for data analysis. These algorithms, they are more numeric computing algorithms than mathematical statistics solutions, because often the solutions to the problems that we try to address, they are not analytic solutions. There is no analytic solutions to them. Then, after this period here, I went and lived in New Zealand for several years. And in fact, I went to, I got my PhD in New Zealand, in Hamilton, the North Island. The name of the university is University of Waikato. Then I went to the United States. I first arrived here in northeast part of the United States, in Pennsylvania, and I worked there for a while. And now I have been in Texas for almost 20 years. My PhD I got way back. So my PhD I got about 25 years ago. I also write, let me see if I switch. I can go to here. I also write this blog, Health Correlator, which is a blog that looks at health data from a statistical perspective. So it's basically it's a blog that has gotten quite a lot of attention. It's more than 3 million views so far. And I analyze using WarpPLS a study that is very famous in the field of health called the China study. I also, I'm having the WebEx is actually showing on top here of the browser. So this is why I'm having trouble getting to the browser screen. But here, I also write this blog called Warp Investor, which is about analyzing data and doing simulations to analyze financial data. And which, by the way, got me to go to, I was curious about how Qatar would be doing now with natural gas and oil prices going up so much. And this is an ETF, exchange trade fund, that tracks Qatar's index and is doing quite well. Historically, is actually has plenty of room to go, it seems. But of course, the best time to buy is here, right? March 20, that was when we had the peak of the pandemic, the initial pandemic scare. And but it seems to be that the Qatari economy is doing quite well. And in fact, one can actually purchase a piece of the economy, shares of the entire country, by purchasing shares of this fund called Q80 CAT. On WarpPLS, so here's the screen for WarpPLS. So most of the things that I'm going to talk about, they are discussed here in multiple forms. I have a number of YouTube videos that are available. I have a large list of publications here on all kinds of issues, including several empirical studies employing WarpPLS. And these have been, many of these have been published in the top journals in various disciplines. And there is also an area, doctoral dissertations. So we have some doctoral dissertations here for doctoral students to use as models. And we have an area of resources with several sample data sets. And I'm going to, today, I'm going to do a little demo using one of these data sets. It will be this one here, equilibration moderation simulated data set. So if you want to follow, you can download this file. Maybe don't, because you may end up falling behind if you try to do it this now. But if you want to redo what I've done today later, you can download this file. It's the equilibration moderation simulated data set. I also have WarpPLS open here. And I hope WebEx is not going, okay, WebEx is letting me go there. I may have to minimize WebEx in a little bit so that I can make sure that it doesn't interfere with the screen. I just don't want to do anything on WebEx and close it by mistake. So, but before I get to the demo with WarpPLS, I want to talk a little bit about some concepts. And my goal here in this presentation is to help you use WarpPLS to do empirical analysis that will allow you to publish in very selected journals. And these journals, they will pick on certain things. So this is what I want to cover conceptually before we go to the demo part. So I'll use slides for that. And let me maximize this. and I will use a pointer. So Colette, so far so good? Can you hear me?
Yes, sir. So far, so good.
Very good. So let me talk about three issues that are really, because Khaled mentioned that he did research, he did analysis using Amos, Liz-Rowe. That's a different type of structural cohesion modeling that's normally called covariance-based structural cohesion modeling, or CBSEM, also referred to as maximum likelihood SEM. And one of the most critical issues today that selected journals will bring up when you say, well, I'm doing my analysis using PLS-SEM, is they're going to say, you're going to use composites, and composites lead to biased results. Now, that is a correct claim, and WarpPLS implements factor-based algorithms that get you results that are nearly identical to the results you would get with Liz-Rowe or Amos or any other tool. Give me 1 second to turn off this phone. Good, I'm back. So they're going to say you're using composites. Composites lead to biased results. WarpPLS implements factor-based algorithms that give you results. They're nearly identical to the results you would get with Liz-Rowe and Amos, but it will estimate latent variables. And Amos, Liz-Rowe, covariance-based SEM in general algorithms, they don't estimate the latent variables. So you don't have latent variables estimated. They estimate loadings, they estimate correlations, path coefficients, but they don't estimate the latent variables themselves. Many people don't know that about CBSEM, but that's at the source of the complication of using CBSEM. Another problem with CBSEM is that you have to create a matrix of second derivatives of a function, a maximum likelihood function on the parameters, and that's called the Hessian matrix. And you have to invert it, and that usually leads to problems for convergence. So WarpPLS implements factor-based SEM, but without those problems. You can have very complex models. They almost always converge, virtually always converge. And so this is a solution to that problem. And two other issues that are asked also are the issue of endogeneity, how to address test and control for endogeneity, and common method bias. So you can address all of these issues with WarpPLS, and I'm going to show you how to do that in the demo, but I'm going to talk a little bit about them here on slides briefly. So the main article on the on this issue of how to do factor-based PLS-SEM is this one, published in the Information Systems Journal, From Composites to Factors, which is available from that website. And this one is also covers that, but it's a little bit easier to understand, but it doesn't have all the mathematical details that this one has. This was published in the Australian Marketing Journal. So this is a typical SEM model, right? So you have the latent variables. Some may be reflective, other may be formative. And these latent variables, they are associated with indicators, which are shown here. So these are the indicators. These are the indicators for latent variable A. And these are indicator error terms, which are uncorrelated with anything, except when there is common method bias. Then they are correlated. And that creates some issues, which I'm going to talk about in a little bit. So the SEM model is made up of the structural model and the measurement model. The structural model is also called the inner model. The structural model is basically the latent variables up here. see if I turned off. Can you hear me now? Can you hear me?
Yes.
Yeah. So I got a chat message saying I cannot hear. Is that everybody or maybe just one person?
Yeah, maybe just one person. Sometimes depends on the internet connection, or maybe his, speaker is low.
Okay.
From our part, you are okay so far.
Good. So let me continue. Oh, I got the okay now from that person. Good. So the structural model is basically, let me change the pointer. So the structural model is basically the latent variables and the links among latent variables. These terms here are structural error terms. Typically, they are uncorrelated with anything except when you have endogeneity. When you have endogeneity, they are correlated with the predictors of an endogenous latent variable. So there is a way to address that with WarpPLS. The measurement model is essentially the latent variables and the indicators, and it is independent from the structural model. And by the way, the structural model is the theory. So when you come up with a theory and want to test that theory, you summarize the theory through the structural model. The measurement model is independent from the theory. It's how you measure the variables. And typically, latent variables are measured through quantifications of question statements and questionnaires answered on Likert type scales. So that gives the structural pressure modeling a lot of flexibility because you can study almost anything by asking people questions. But the problem with asking people questions about constructs is that your measurement will be by definition with error, right? So for example, let's say you want to measure job satisfaction. You can measure it reflectively by asking redundant questions of the type, I like my job is great, to be answered on Likert type scales from, say, 1 to 7, strongly disagree to strongly agree. You can measure it informatively by asking non-redundant questions of the type, I like my boss, I like my office. So these are redundant, right? I like my job is great. The answers to these questions are expected to be the same. Answers to these questions here, maybe not, because some people may like their boss, but not their office, and vice versa. Now, here's a very important issue. In both reflective and formative measurement, the construct, job satisfaction in this case, exists in the mind of the researcher before any question is devised in the questionnaire. So if you want to measure job satisfaction, you have job satisfaction, the idea in your mind before you come up with the questions. You will not come up with a question, I like my dog, thinking about job satisfaction, right? Because job satisfaction is the motivator, is the idea that leads you to come up with a question. Because of that, the latent variables always cause the indicators. I know there is a lot of debate on this. Some people say that when formative measurement is used, the indicators cause the latent variables. That's not actually true. For the indicators to cause latent variables, you would have to come up with questions randomly and then aggregate them, but that would not even be the indicators causing the latent variables. You would come up with an index. You can come up with indices, but like the S&P 500, the Dow, and so on, but not when you use questionnaires. When you use questionnaires to measure latent variables, the LVs always cause the indicators. Same thing with other types of, this is a more concrete example. electronic communication media used. So I could measure it reflectively by asking questions at the time. I use econ media. Using econ media is important to me. Or formative, I use email, I use video conferencing. Note that formative measurement, all of the question statements, they are related to the construct, but they address different facets, different dimensions of the construct. So do LVs cause indicators? Yes, always. That's my opinion. I know there is debate on this issue, but if you don't assume that this is the case, then you cannot do factor-based. You cannot come up with a factor-based approach to do SEM using PLS algorithms, and then you cannot get the same results that you use with Lismer and Amos, because Lismer and Amos assume that you deal with factors. So when the LV causes the indicators, you have a factor. When the indicators are assumed to cause the LV, then you have what's called a composite. And that's what traditionally is done in classic PLS. So PLS mode A, PLS regression, these are all composite-based algorithms. Factor-based PLS algorithms, they are different. They are more like Lisrow and Amos in their estimation. So when the latent variable causes the indicators and you regress the factor on the indicators, you get weights, right? When you regress the indicators on the factors, you get loadings. Typically, you expect loadings to be high. So you get weights, but then something else emerges, which is this measurement residual, which has a weight as well. So factors are an aggregation of the indicators and of something else called a measurement residual, which could be seen as a separate indicator. So that's the difference between composites and factors, right? With composites, you have just the indicators used to approximate the latent variables. With factors, you have the indicators and measurement error, measurement residual, used to approximate the factors. By the way, when you regress the factors on the indicators, an R-squared emerges, and that R-squared is actually the true reliability of the factor, which is measured through Cronbach's alpha, but measured with imprecision with Cronbach's alpha. WarpPLS also calculates the true factor reliability. Now, let's talk a little bit about endogeneity. So what is endogeneity? Endogeneity happens when the structural error terms are correlated with the predictor. So, and this is for endogenous variables. So endogenous LVs are LVs that other LVs point at. So this is endogenous. This one is endogenous. This is endogenous too, even though it has only one predictor. This is not. This is exogenous. So this is not an endogenous LV. And what causes endogeneity is LVs being a cause indirectly of endogenous LVs, but not pointing at them directly. So, for example, for LVD here, that's an endogenous LV, it gains variation indirectly from LVA. Indirectly. But LVA does not point directly at LVD. And that causes endogeneity. And the way to address this problem is to create instrumental variables that will capture that variation from the variable that points that transfers variation to this, but does not point at it directly. Now, you may say, why don't you create a link between LVA and LVD? The problem is solved. It's not, because if this is your theory, your theory is stating that there is no direct link between LVA and LVD. So you're theorizing the LVA transfers variation throughout LVD via these mediators here, LVB and LVC. And so if you create a link between LVA and LVD, that link will probably be associated with a non-zero path coefficient that may even be statistically significant, which means that you're going to end up with a false positive, which is incorrect because that is not part of your theory. So you're not going to be testing your theory. And this is how it's done in WarpPLS. So you just create an instrumental variable. I'll show how to do this now. Now, common method bias, very briefly. Common method, and by the way, common method bias is the ultimate problem. It's a problem that currently there is no numeric solution. I've been trying to come up with a solution that is numeric for it for a couple of years now. And I can tell you it's extremely difficult. Doing factor-based PLS-SEM is easy compared to solving the problem of common method bias. So what is common method bias? Common method bias is a phenomenon that's caused by the measurement model used in an SEM study and not by the network of causes and effects in the model being studied. And for example, instructions at the top of a questionnaire may influence the answers provided by the different respondents in the same direction. This is the common bias that we're referring to. Cause the indicators to share a certain amount of common variation. Another possible cause of common method bias is the implicit social desirability of associated with answering questions in a questionnaire in a particular way. But, let me give you a simple example. Let's say I have a simple model here, technology affecting job performance. And then I give 100 questionnaires to 100 people. And in the questionnaires, I have questions about technology and performance, okay? And let's say, just for the sake of discussion, that I tell these 100 people, that I tell them this. People, please exaggerate your answers a little bit. Answer a little bit higher the technology questions and a little bit higher the performance questions. If I did that, I would have induced common method bias. And that's represented in this way. So the indicator error terms, they are not uncorrelated. They are correlated because they are dependent on this M variable here, which represents the common method variation that is shared, and that is shared because I made a mistake in my data collection. Another thing that would induce common method bias is you do a study like this and you tell people in an organization, we are using a new technology here because we wanted to increase job performance. Please use this technology a lot. And then you give them a questionnaire for them to answer whether they use technology or not and to what degree. And then you say to them, and by the way, return your questionnaires to me. Your answers are anonymous, but return them to me. So they will, the respondents will implicitly, they will subconsciously realize that the questionnaire is not really anonymous. So they will exaggerate their answers for technology and performance. Who would want to say that their performance at work is low, right? So everybody will exaggerate their responses for indicators for performance and technology, and then you're going to have common method bias. Now, I will show you, let me just show you, I created previously a model with common method bias and without, two models. And this is essentially the model. So 3 latent variables, 6 indicators each. And here's some of the things that happen with common method bias. So the path coefficients, they get inflated. So with no common method bias, you get these path coefficients here. you know, that are, the data is clean, free from common method bias. So I have 0.45, 0.36, 0.41. With common method bias, the path coefficients go up. So 0.63, 0.44, 0.51. So they go up. So one could say, hey, common method bias makes my data look better, my results look better. Yes, that's true, but review panels in selected journals, they will want to test for common method bias to rule out these types of problems. Loadings tend to be inflated with common method bias as well. So no common method bias, I have loadings of 0.7 or so. With common method bias, they go up to 0.9. So again, makes my measurement model look very good. So common method bias is a real problem because of that. It may actually make you support a theory that is completely wrong because of these better results. And the way we address or we test for common method bias is a new test that relies on focal linearity variance inflation factors, which are calculated for all latent variables in the model, and they're calculated through this formula: 1 divided by 1 divided by 1 minus the R squared, where the R squared is calculated for each LV when we regress that LV on all of the other LVs in the model. So this has been proposed recently and has gotten a lot of citations. My article on this method has more than 1,500 citations. Just that one article that was published, I think, in 2017. And this is a method that has been proposed. So what we do is we compare these focal linearity variance inflation factors with a threshold. Often the threshold 3.3 is used, 5 can be used as well. And this method was proposed as a replacement or in addition to Harman's single factor test, which you can also do with WarpPLS very easily. And this test entails actually creating one single latent variable that aggregates all of the indicators in your model, and then comparing the AVE at latent variable with a threshold. Threshold is usually 0.5 for Harman's single factor test. This test here, using focal linearity variance inflation factors, seems to be more sensitive to common method bias. So this is why it's been widely cited. So I will stop my PowerPoint presentation now, and I will go to the demo parts. And I guess we're good in terms of time, right? Right, Khaled?
Yeah, that's fine.
Okay. So the sample that I will use for this, I will do a full analysis. So I'll use that sample data set that I pointed at earlier in the presentation on the website. But before that, are there any questions that are burning questions that you would like me to answer before I go to the presentation part? No, so let me go to the presentation. So WarpPLS is easy to use because it allows you to do an analysis through steps. And I'll go to the beginning, step 1, which is the step in which I will create a project file. And I will create a project file, I'll call it temp.prj. And I'll just overwrite a file that I already have there. Minimize the stuff in the back. So, okay, so I have. So then I will go to step 2. And step 2, oh, by the way, let me show you that Excel file. So this is an Excel file that has 3 sheets. One is the true model. I say this is a true model because I created this model using the Monte Carlo simulation method. And so I know that this is the true model. And as you can see, you can have a true model where you have a moderating effect without a direct effect to that same variable that is being influenced by the variables. So this is the true model. It has a moderating effect. And in the first sheet on my data sets, I have the numeric data. So I have 300 records that I created. So this is the numeric data that I will be reading using WarpPLS, the one that is on the first sheet. So I'll go to read from file. I can also read from the clipboard. I'll read from file. So I will go to that. I will choose the new Excel format. I will double click on that file. I will click OK. I'll try to go slowly here for those who are trying to do this together with me. But if you fall behind, don't worry about it. So the software is taking a little bit here to read the file. Just wait. Let's just wait for it. I have several applications running in the background, so this is why it's taking a little longer. So here the software shows me this import wizard. All I have to do here is to click on next and finish, nothing else. Then the software shows me the data that was read. It's usually a good idea to take a look at the data when you get it, because sometimes you have corruption in the Excel file. And by the way, you can read from text files with tab delimitations as well as comma delimitations in between fields. So the data looks okay. This is the raw data. So it's a Likert type scale data. So I'll click on yes. Then I'll go to step 3. And one of the main things that is done in this step 3 is it will impute missing data, because you should not delete data if you have missing data, unless you have the entire column missing. I'm sorry, entire rows missing. But if you have sparse missing data, you should keep the missing data and let WarpPLS impute that missing data. There are several algorithms that the software use for that, and you can see these here in settings, view or change missing data imputation settings. I will use the default algorithm, but the best one for WarpPLS is multiple regression imputation. I've tested this before. And believe it or not, multiple regression imputation can give you relatively reliable results, even with 50% of your data set missing, as long as the missing data is sparse. It's not like one row missing, another row missing. It's sparse missing data. But I'll leave the arithmetic mean imputation, which is not the best for this. So I'll go to pre-processed data, and the software will tell me that it will check for missing values, and then there are no missing values in this data set. But if there were, the software would tell me how many, the percentage, and that it fixed that. And then it standardizes the data. Standardizing the data helps with the computational complexity of the algorithms used in the software, reduces that complexity, which leads to less standard errors. So the software ends up yielding more statistically efficient results than software like LISRO or AMOS, which is very complex, the calculations that they perform. So I'll click yes here. So step 3 is just basically taking care, preparing the data for the analysis. Now I will go to step 4, which is to create the model or define the SEM model. So here's where I'm going to create my latent variable. So I'll just go to latent variable options, create latent variable, and I'll create one of my latent variables. This one is going to be job satisfaction. Another latent variable, which is going to be electronic collaboration media use. This simulated data, it assumes that I collected data at the group level of analysis. So 300 groups performing a complex task. The next variable will be project management, the extent to which the groups or the teams use project management techniques. None of these variables is formative, but if any of them was formative, I could click on formative and then define it as formative. Go to reflective. I'll create another variable. This one will be success, my main dependent variable in the model. And it will be measured through. Very easy, right? This job satisfaction in this model is actually a control variable. This is how you control for effects with respect to a dependent variable. You just create them as variables and then you make them point at that variable. Now I'll create direct links among the variables. And I'll create a direct link here for the control variable. And remember, there is no direct link here from that model that I showed you before, but I will create a moderating link between this variable and this one. To create moderating, to analyze moderating effects, it's very hard to do using CB-SEM, because CB-SEM, as I mentioned before, does not estimate the latent variables. So I will save my model. And one thing that I will do is I will go to the option View or Change General Settings. And I will leave I'll choose a factor-based algorithm, but I will show you the algorithms available here. So all of these below PLS regression, they are composite based. And all of these up here are factor based. So in this community that do research on methods and PLS-SEM, there is debate now. And there is one group that thinks that you should always do composite based. There is another group that is moving in another direction, and that is my view, is that you should, as long as you can, factor-based algorithms. But if you submit to a selected journal and the review panel says, we want you to use a composite-based algorithm, you're not going to get accepted if you tell them, oh, sorry, I don't agree with the review panel. I will use a factor-based algorithm. What will happen is that the next round of reviews, you will all come reject, 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 and your paper will be rejected. So you can always do a composite-based analysis and then do a factor-based analysis, including in the appendix, and say, I'm doing this because I believe that factor-based algorithms give more correct results and so on. I will choose for this analysis this one, factor-based PLS type CFM3. Each one of these algorithms is discussed in the user manual for the software. And the user manual you can get from their website directly or from the help, any help area of the software, you can get the user manual, right? So you just click here and a PDF file opens on a browser window. So I will choose this one, CFM3, which is the one that most closely resembles the covariance-based SEM technique. And here, one thing that WarpPLS does that's quite unique is that it allows you to do nonlinear analysis. But what I normally do is to start with a linear analysis. In a linear analysis, your effects, the gradients, which are the path coefficients, they are fixed, right? Nonlinear analysis, there are two types, warp 2 and warp 3. Warp 2 assumes that there are instances of self-moderation in the model, and warp 3 assumes that there are instances of double self-moderation in the model. I'm not going to go into a lot of detail on that in this presentation. I'm just going to focus on the other issues. But I normally recommend that you start with linear, and then you go that, and you can actually set individual paths as nonlinear. But just if you ever used SPSS and did multiple regression, you'll probably recall that they have fixed effects and variable effects. Sometimes they call it, I think they refer to it as random effects. That's actually nonlinear. So when you use a random effects approach, you are doing a nonlinear analysis. What WarpPLS does is it assumes that you are hypothesizing the type of nonlinearity you want to test for. And that refers to self-moderation as well as double self-moderation. So I will save these settings. And I will conduct my analysis. And here are my results. So the moderating effect is all of the effects are significant in this particular analysis. And if I go here to view, I get a number of results, right? The path coefficients that are shown on the screen, I can get them with a bit more precision here. I can get loadings and cross loadings. So here you can see my loadings. Typically, you want to see loadings greater than 0.5 for convergent validity. They seem to all be good in that respect. And you have a number of other results here that allow you to test for a bunch of different things. You have plots, plots of the relationships themselves, various different plots with and without data points. And for the moderating relationship, you also have plots. Since moderating relationships are actually 3D types of relationships, you have 3D graphs that you can rotate to get a better view of the data. But you can also show the relationship using other graphs, 2D graphs. For example, this one here without the data points. You can also see a graph with the data points. And you can also see these two separate graphs with data points. You can also, typically when you have these graphs, you split the sample in the middle, but you can change the split. So 0.50, you're splitting in the middle. If you change this number here, you're splitting it with fewer points here. So 25% of the points here and 75% of the points there. If you go the other direction, then you have fewer points on the right and here on the left. Any questions so far? Can you hear me?
Yes, they cannot, I think, they are mute, so they can only ask through the chat.
Okay.
And
so
I'm monitoring. So far, no question except that if you are willing to share the presentation, but also we are recording this session, so it will be available on our website, the QDSI, Qatar DSI chapter. So they don't
Good,
worry
good.
either way.
Okay, so we're good in terms of questions. So let me continue then. So let me address the issue of endogeneity first. So here's the problem. I have one variable here that influences this endogenous variable indirectly, right? So it influences this variable success indirectly via the moderating effect and also via this mediated relationship here. And because of that, there is a risk that I may have endogeneity. In reality, endogeneity doesn't really come up, it doesn't really occur in models that are simple as this one. More complex models where you have several variables indirectly affecting an endogenous variable, then those are more likely to have endogeneity. But in a selected journal, they may say, well, you have to control for endogeneity. And again, if you create a direct link here, you're going to be adding a link that doesn't exist at the population level. It doesn't exist in reality. So you're going to get a false positive because these two variables here are correlated. I can even check their correlations. So view correlations among latent variables. So you can see Equalab and success, they are correlated. And this is going to be significant if the path coefficients of similar segment magnitude with a sample size of 300, this will be significant. So you will end up with a false positive. So to address endogeneity, you have to create something called an instrumental variable, which is a variable that is uncorrelated with anything in the model other than this variable here, which is called the instrument in this particular situation, and nothing else. So it will contain variation from the instrument that ends up on the endogenous, in the endogenous variable, and nothing else. You'll be uncorrelated with everything else. So how do I do that? I go to Explore, Analytic Composites and Instrumental Variables, and I choose to create an instrumental variable. And the instrument that I will use for that is Ecolab. And my endogenous variable that could be affected by endogeneity is success. So I will then click on yes. And this is the name of the variable that will be created. It will be added to the data set as an indicator. So I'll create this instrumental variable. Then I will go to the model, define model. And what I will do is I'll create a new latent variable. That will be that instrumental variable. I have 8 characters for each latent variable. So that's why I'm creating with the same name as the indicator. Save. And then I will make this instrumental variable point at my endogenous variable. Now you see, project management is endogenous too, but there is no problem because in reality, at my population, e-collaboration directly points at project management. So there is no problem of endogeneity with respect to project management, even though it is endogenous. The problem is here with success because this variable indirectly transfers variation to success, but does not point at it directly. That's how endogeneity emerges. So I'll redo my analysis. And I get these results. So as you can see, the path coefficient is very small. It's non-significant. The p-value here would have to be below 0.05 to be significant. So this these coefficients tell me that endogeneity is weak and not significant. So if I didn't control for it, it would not affect my results in the model. But I controlled for it. So I can say that I'm also controlling for endogeneity in my analysis. Now, let's test for common method bias. So save project. So I'm going to test for common method bias, super easy using that method. So that I mentioned before. All that you have to do is go to view save analysis results, view latent variable coefficients, and then take a look at these coefficients here. Focal linearity variance inflation factors. If you use factor-based algorithms, my recommendation in that paper is that you use the paper that I mentioned to you, is that you use as a threshold here 5. So as you can see, there are no focal linearity variance inflation factor VIFs greater than 5. Therefore, I can conclude that my model is free from if I used a composite-based algorithm, my threshold I would recommend to be 3.3. And these recommendations are in that paper that I mentioned to you before that received a lot of citations. So that's essentially what happens. Now, if so I'll save this project. Save. Now, if I let me show you a model that has common method bias. So I'll open a project file. This one has common method bias. So it's a different model that I created before. And so when I go here to view and save analysis results, and this is a composite-based algorithm. If I go to view, so the algorithm that I use here is, if I go to general results, it tells me what the algorithm is. The algorithm used is PLS mode A. This is the most commonly used algorithm for PLS-based SEM, classic PLS-based SEM, composite-based. So in this case, I would recommend a threshold of 3.3. So if I go to my view latent variable coefficients, I can see here that this focal linearity VIF is actually greater than 3.3. So this is an indication of common method bias. And indeed, this data set has common method bias in it. It's not a lot, it's a medium level common method bias. And I know that because I created the data set with common method bias. So this addresses all of the issues that I wanted to address in this presentation. So right now, I think it would be a good time for us to have some Q&A, right? Because we're moving toward, I guess, the end of the time for this presentation. So I will open up to questions. I'll take any questions at this time.
Okay, yes. Anyone who would like to ask, you can raise your hand, so we'll give you the mic. Is there anybody? Okay. We can hear. One? Yes. خليك تطلع صوت.
Hi there. Hi. Thank you very much, Professor Ned, for a really interesting, really interesting presentation there on WarpPLS. I must say, I still think that you've combined both composite and factor analyses, which is which differentiates WarpPLS from Lizroll and possibly Amos. So my question to you is this: how likely is it that you will? Because I've seen a few papers recently that say, you know, that go either ways, right? How likely is it that we will stamp on reviewers that would be on one camp or the other, and how do you deal with that? You know.
Well, the issue you may face is reviewers saying that composite-based analysis lead to biased results, right? And if a reviewer says that in a selected journal, so let's say you submit to a very selected journal, one of the top journals in your field, typically they will have a few reviewers, and in these journals, editors are very risk averse. So if they get a very strong rejection from one of 4 reviewers, they will reject. And so the advantage of doing both analysis is that you can say yes, you can even say I don't agree with that, but I have done both types of analysis, factor-based and composite-based. And who knows, you could even try to do it via Lizroll and Amos, but the problem with those tools is that they often don't converge to solutions in many models, and there isn't flexibility on the types of tests you can do. Right? For example, moderating effects analysis is very difficult to do. But I would say that given the debate that is happening in the field, and I am one of the people that are participating in that debate, right? In fact, there is an article coming up on the communications of the EAS, which is very critical of composite-based SEM and classic composite-based SEM. And so that leads more and more reviewers to be inclined to ask for factor-based analysis as well. And by the way, this paper that is coming up on CAIS, I've been asked to write a rejoinder for it. So there will be, in the group of papers that will be published in that issue, one of the papers will be mine, and I'll be talking about these things that I talked here. But I would say it's likely that you will find reviewers that will question. I don't know what the probability is, but I've faced that a few times already, and myself. And you're doing the factor-based analysis usually leads to positive results in the review process. Review process. So for selected journals, handling the review process is almost as important as being a good researcher. You have to really treat the reviewers as demigods in a sense. So you can never question the reviewers. You have to, even if you disagree with them, you have to say that in a way that is indirect and provide more coefficients, more analysis. And one of the advantages of WarpPLS is that it provides a lot of different types of analysis results, right? Many features.
Thank you, Ned. Thank you.
Okay, we have another question. Go ahead.
I want to ask about common method bias. Just like you said, common method bias can be caused by different methods. Method measurements that you have. Probably it could be desirability problem. It could be the way you ask the questions and all of that. So using this full collinearity variance inflation factor, does it control for all the methods? Measurement error that you could have in terms of whether it's the social desirability or the anchoring problem or the type of question you ask. Does it control for all the categories of common method bias problem you may have regarding the methods you choose?
Well, well, first of all, I should tell you that there is no solution for common method bias that is widely accepted, right? So if you find that your data has common method bias, currently it's very difficult to address that problem. There is a little bit of a trick that you can employ to reduce the amount of variation shared in the model, but there is no guarantee that that really solves the common method bias as it originally existed, okay? In other words, you can reduce your FCVIFs in the model, but you cannot say that by doing that, you provided a correct solution to the common method bias problem. You're basically reducing collinearity if you do that. And it's a little tricky. I can even show you how to do it here. But to answer the other part of your question, yes, the focal linearity variance inflation factors, they will capture all of the sources of common method bias because the contamination will come through the indicators into the latent variables, right? And the latent variables, they aggregate indicators and therefore the common method bias that is contaminating them. So arguably, these focal linearity variance inflation factors, they are the best, most sensitive indication of common method bias. Now, here's one thing that you can do. So let's say you have this model, it has common method bias, right? So you go to your latent variable coefficient. So this VIF is too high, right? So how do you reduce this VIF? You can do this, and it's a bit tricky. What you do is you remove variation from the model following the theory that you're using. So the theory is essentially the model. So the theory is that these latent variables are connected in this particular way. So you remove variation from the model consistently with the theory, which means that if you want to remove variation from ADVT, this variable here, which is the one with the high FCVIF, what you do is you remove a little bit of variation in it that comes from tech and collab. How do you do that? I will save this as temp because I don't want to mess up that previous model. So what you do is this. So let me open an Excel file so I can store those previous. So I'll store in this Excel file, store some of those results. So if you recall here, I had VIFs, right? So let me just, so this is my VIFs that I had. Now I'm going to remove variation. So I will remove variation by essentially creating an analytic composite that I can use as a replacement for ADVT. And this analytic composites, first I'm going to do something else. First, I'm going to do something else. I'm going to go to modify, and I will add all my latent variable scores as new standardized indicators. And then I will modify my model by using those scores. So it's like a second level type of analysis. I will modify my latent variable by replacing my latent variables by replacing them with those latent variable scores. I will not have the indicators anymore. So I'll remove the original indicators contaminated with common method bias, and I'll replace them with the latent variable scores. This will not initially do anything, but then after I do this, I will be able to imply that procedure. So I will save my model. I redo my analysis. So I have the same results. I still have the contamination, right? So I still have that high FCVF. But what I'm going to do now is create an analytic composite that will contain variation from these three variables. So I will create an analytic composite that will contain variation from this, this, and this. So I clicked on them. They're shown here as my indicators that I will use. So I want an analytic composite that will replace ADVT, and that will have less variation from tech and collab than I had before. And the way I do this is by assigning negative weights, weights there of negative of reverse sign of the original weights. So I will add very small weights here, negative. So I will use a tiny amount of variation coming from those variables by assigning these. So as you can see, the variable that I am going to create here as an analytic composite is very highly correlated with my original ADVT. So if the correlation with it is 0.999, it's very highly correlated. So it's redundant. It's almost identical with that to that variable, but it will have a little bit less variation from them, and that will be reflected in the focal linearity variance inflation factors. So I'll click on yes, and I will create this analytic composite that will be used as a replacement for go back to my model, and I'll use, instead of this variable, I will use that composite that I added to my model. And then I'll save my model and redo the analysis. And now I should get focal linearity variance inflation factors that are a little lower. So you see, now it's below the threshold. So this is what I had before. I had, this one was above the threshold at 3.3. Now it's below 3.3. So now my model arguably is free from common method bias. Now, you could say, well, this looks pretty good as a method, right? The problem is that the way I'm removing variation is not as perfect as I want it to be, because what I want it to be is for this method to remove variation exactly in proportion to the variation that came through common method bias. And that's what I've been working on. So I will probably have in future version of WarpPLS, future versions, I will have a more perfected and easier variation of this technique that I just demonstrated to you. But as you can see, I can reduce multicollinearity in the model by doing that operation and creating analytic composites. It's a complicated procedure, I have to admit, but it seems to work in terms of reducing those coefficients.
All right. Yeah, thank you so much for your demonstration. Thank you.
Okay, we have another question from the chat. Ned, can we use this software with the binary or nominal data, type of data?
Yeah, yes, you can, but there is always some loss, right? So when you use dichotomous data, right, say male, female, and then you dummy code that 0 and 1. Yes, you can include in the model. Now, one thing that you should keep in mind is that if the variable is endogenous, it's an impossibility that you can have that in real life, right? So you have to understand that you're going to have bias if you do that. So what I mean by that is this. So what do you do? So let's say you have a variable that is biological sex, right? And you are arguing that biological sex is influenced by certain conditions that are defined by a variable that is itself dichotomous, right? So A is dichotomous. The problem is that you always have an error term, and the error term is not dichotomous. The error term is on a ratio scale. So a variable that is caused by other variables in the model, if it is dichotomous, you have to understand that what you're doing is you're replacing the true variable with something that is not the true variable, because an endogenous variable cannot be dichotomous. Now, there is an approach to deal with this, which it's not really implemented in WarpPLS, but it is something that I want to implement. And there are some tools here that could get you some way toward implementing it. And that is to replace a dichotomous variable with another variable, which has a distribution that looks like a sigmoid or a logistic distribution. And then use it in the model, and then what you would do is something similar to a logistic regression. And that variable would be a probability, right? Because you can say, yeah, sex is influenced by another variable, but it's not dichotomous. But the probability that you're going to have male or female as a sex, as an outcome, that is perfectly okay, but it's not going to be dichotomous, right? It's going to be rational, and it's going to be a probability. This is not implemented in WarpPLS yet, but you can do that in a roundabout way by exploring conditional probabilities. And you can actually calculate some points, and then using Excel, you can actually then create that probabilistic distribution and then use that in place of your dichotomous variable. Now, for endogenous variables, that's not an issue, right? Exogenous variables can be dichotomous. And you can also control for effects that are dichotomous, right? Control for gender, for example, for biological sex, for example. So yes. Now, if you dichotomized a variable that originally was on a ratio scale, say, for example, job performance, instead of using job performance on a ratio scale, you just use high and low. That is not a natural dichotomous variable, right? You're dichotomizing it, and by doing that, you're gonna lose information, and that will tend to lead to a suppression in the path coefficients. Now, one thing to keep in mind is that, let's say this variable here was, I dichotomized it, and it is endogenous. What would happen is that these path coefficients here would be suppressed. So you could say that if you use dichotomous variables in a model, your test of the model will be more conservative. You're probably going to be making more false negatives than more false positives. Okay?
Okay, thank you. We have one more question.
Yep. Thank you very much, Professor. Really enjoyed your presentation. Coming back to the last question on common method bias, I think you mentioned that we'd not have any mathematical solution, right? But what we could maybe potentially have is, when we control the method. So for example, like the example that you gave on technology and performance, I don't think if we don't have a mathematical solution, maybe then we can, if we control the process, maybe that's the solution to reduce the common method bias. What do you think?
Yes, absolutely. In fact, most of the solutions to common method bias that are proposed, they are pre-common method bias, right? I'm sorry about this phone. I thought I had turned it off, and now it keeps on ringing. But anyways, so most of the solutions for common method bias that are proposed, they are pre-data collection, right? So, do the data collection in a way that avoids common method bias. And yes, you can do that, but it's very difficult, right? It's very difficult for you to ascertain, particularly if you collect field data. Experimental data and data collected in a lab experiment, it's not as much, but if you collect field data, it's more complicated. By the way, I'm working on a solution to common method bias that is not the ideal one, that would allow you to actually extract common method bias from the model, but you would have to collect data twice. So you would have to collect data first using something like Amazon Mechanical Turk or something like that. And then you would collect data for your latent variables individually. And then you would use the loadings to extract common method bias. So let's say you collect data from multiple environments using Amazon Mechanical Turk. And then you collect data in a field setting, and that data has common method bias. Using this approach, I am going to be able to extract common method bias by making these loadings collected in the field identical to the loadings that are from data that is not contaminated by common method bias. Now, there are approaches that you can use, but one that I often hear being mentioned, frankly, it's impractical and makes little sense. So the approach that I often, this is something that I often hear people say, since you collect data from the same individual for different latent variables, right? So let's say you have several latent variables, and then you collect the data from the same individuals, that leads to common method bias. So one way of eliminating that is collecting data from different individuals, right? But the problem with that is that different individuals in the same situation may be affected in the same way by common method bias. And you cannot break the link of the unit of causality link, right? So you cannot collect data about technology used by one person and then performance by another, and then try to analyze that data because you broke the link of the unit of analysis. If your unit of analysis is the individual, you have to collect data on all of the latent variables, all the indicators from the same individual. There is no way you can collect from different individuals and still be able to do research. Now, if you have groups, then you can have different individuals from the group. But then the problem is that they may be affected, different individuals may be affected by common method bias in the same way. Now, one thing that you should definitely do is avoid leading questions in questionnaires or avoid instructions in a questionnaire that are leading answers. That would be something that would certainly induce common method bias.
Understood. Thank you.
Okay. Any other question before we end? Almost we are on time. Anybody? Okay, since we don't have any more questions, we would like to thank, Professor Koch And please give him a round of applause.
Thank you. Thank you very much.
Thank you. And as I mentioned, the recording hopefully will be available in a few days on our website. If you go to Decision Science Institute, then Qatar Chapter under webinar recordings, the link will be there. Thank you and have a nice rest of night or rest of day, depends where you are. Thank you again for coming. Thank you.
Thank you. Bye-bye.